In 3.3, we look at some more properties of determinants. And one property of determinants says that if we have determinant, if we have matrix A times B and we want the determinant of that, it's equivalent times the determinant of A times the determinant of B. So let's look at an example and check that. That's assuming that A and B are both square. So let's suppose that A is the determinant 1, 3, 2, 2, and B is the determinant 2, 1, 1, 4. So the determinant of A is 2 minus 6, and the determinant of B is 8 minus 1. So the determinant of A times the determinant of B is -4 times 7, or -28. Now let's find A times B, and let's see what the determinant of A times B is. So if we take A times B, remember we do row times column, and that gives us 2 plus 3. Row 1, column 2 is 1 plus 12. Row 2, column 1 is 4 plus 2. Row 2, column 2 is 2 plus 8. So if we calculate this determinant, it's 50 minus 78, which is indeed -28. So that might come out to be useful. Another property of determinants is if we have matrix A and we multiply matrix A by a scalar, and we want to take the determinant of that, and that's equal to the scalar raised to the nth power times the determinant of A, where n is the rows or columns of A. Now remember when we took a single row and multiplied it times a scalar. If we multiplied a single row by a scalar, let's suppose we multiply it times 3. Then the effect that had was, notice 1 minus 6 is -5. Here, 3 minus 18 is -15. So when we multiplied a single row by a scalar, then it just increased our determinant by that factor. If we call that C, it increased it by a factor of C. But in order for us to multiply A, the whole matrix, by a scalar, for example 3, we would have to multiply the first row by 3 and all other rows by 3. So in this case, we would also multiply the second row by 3. So if we multiply the second row by 3, we get 9, 3. That gives us 9 minus 54 is -45. Notice we multiplied it by 3 and another 3. 3 times 3 is 9. So our new determinant is 9 times our original. So notice what we did. We multiplied our matrix by a scalar. It had 2 rows or 2 columns. So we did our scalar 2 different times and multiplied that times our original determinant. 9 times the value of our original determinant gave us the value of the new determinant. I'll look at this another way. If we have some determinant that's triangular, let's suppose we have that, and that inside is matrix A. Then notice the determinant of that, if we multiply down the diagonal, is 1. But if we take A and multiply times 4, then every component, every entry gets multiplied by 4. 4 times 1, 4 times 2, 4 times 3. And that gives us this determinant. Again, if I'm multiplying this by a scalar, it's still going to be upper triangular. It's diagonal, so we multiply down the diagonal and we get 4 times 4 times 4, which is 64. So notice our determinant didn't increase by a factor of 4, but it increased by a factor of 4 cubed. Basically, a factor of 4 for each of our rows. Hence, to multiply our matrix by a scalar, then it's that scalar raised to the number of columns or rows times the determinant of A. Now, the next theorem that's covered in this section says that if A is a square matrix, it's invertible if and only if the determinant of A does not equal 0. So back when we were talking about solving systems of equations, if I had a matrix, it could be an augmented matrix. I'll tell you what, let's look at it not as an augmented matrix. But if we came up with a 0 row, think about this as AX equals B. Let's use different numbers over here. If we come up with zeros here, then this has no solution. Notice this says no x1s plus no x2s equals 3. Well, how can 0 equal 3? Also, this means that, notice this if we took the determinant of this, what would the determinant of that be? It would be 0. This product is 0 minus this product is 0. So the determinant of that is 0. Also, this matrix doesn't have an inverse. Why does it not have an inverse? If we were to take that and put it in an augmented matrix with the identity matrix, it's not possible to row reduce this so that we get I on the left and then something else on the right. If this has all zeros here, we can't get an I on there because we have a 0 row. So this works both ways. If we know that A is invertible, then we know that our determinant can't be 0. Also, if our determinant is not 0, then we know A is invertible. On the other hand, if the determinant of A equals 0, then A is not invertible. Or if A is not invertible, then the determinant of A equals 0. So all four of those statements go hand in hand. So if we know the determinant to be 0, no inverse, which also is going to lead to the fact that there's no solution to a system where that's the coefficient matrix. Also, if the determinant is not 0, then it is invertible. Now let's look at the relationship between the determinant of A and the determinant of A inverse. Now note that A times A inverse equals I. So let's take the determinant of both sides. Well, no matter what size I is, this is both upper and lower triangular. If we expand down this row or this column, or across this row or this column, or this row or this column, we're going to get a value of 1 for that determinant. Notice if we take this entry times the cofactor, we get 1 times 1 minus 0, which is 1. So the determinant of I is always 1, no matter the size of I. Also, if we take the determinant of a product, we can take the determinant separately. So if we want to know the determinant of A inverse, divide both sides by the determinant of A. So the determinant of A inverse is 1 over the determinant of A, which is sometimes easier to calculate than determining, well, what is the inverse of A, and then coming up with its determinant. If you just come up with A's determinant, then 1 over that is the determinant of the inverse. So, quick example. If we have 1, 3, 2, 1, real quickly, the determinant of that is 1 minus 6. So we would expect the determinant of A inverse to be 1 over that. Well, let's real quickly get A inverse. And remember, the shortcut for getting A inverse is to swap these, take the opposite of these, and then do 1 over the determinant here. So 1 minus 6 is negative 5. Did I do that correctly? Yeah. So the inverse, if we take this times that matrix, is negative 1/5. So where were we? So negative 1/5 times negative 3 is 3/5. Negative 5 times 2, negative 2 is positive 2/5. Negative times positive is negative 1/5. So if we take the determinant here, we get negative times negative is positive 1/25 minus 2/5 times 3/5. 2 times 3 is 6. 5 times 5 is 25. So negative 5/25 reduces to negative 1/5. So this was A inverse. This was the determinant of A inverse. Notice the same thing we got when we calculated the determinant of A and then did 1 over the determinant of A. So much quicker if all we're needing is the determinant of A inverse. So the last thing mentioned in this section, we've been collecting equivalent statements as we go. So all of the following statements are equivalent for an n by n square matrix. A is invertible. The system AX equals B has a unique solution for every n by 1 column matrix B. So for every different B, this system has a unique solution as long as A is invertible. The homogeneous system only has the trivial solution, and that is where X equals 0. A is row equivalent to the identity matrix. Basically, we can take A, row reduce it, and get the identity matrix. A can be rewritten in terms of elementary matrices multiplied together. Written as a product of elementary matrices. So that's the list we've already had, and then the new one that we just picked up was that the determinant of A is not 0. So if we have one solution, if our coefficient matrix is invertible, if the only solution to the homogeneous is 0, if A can be reduced to I, if A can be written as a product of elementary matrices, if any one of these is true, then all the other ones is true, and the determinant of that coefficient matrix is not 0. So something that might be useful as we work along the way.